reject of losses and risk. In some application, wrong decisions, namely misclassifications, may have very high cost, and it is generally required that a more complex, for example, manual decision is made if the automatic system has low certainty of its decision. For example, if we are using an optical digit recognizer to read postal codes on envelopes, wrongly recognizing the code causes the envelope to be sent to a wrong destination. Now, this is what we call a reject. A possible loss function is lambda ik equals to 0 if I equals to k, equals to lambda if I equals to k plus 1, where lambda belongs to 0 within a limit of 0 and 1, or else it's 1. This 0 less than lambda less than 1 is the loss incurred for the choosing of k plus 1's action of reject. Then the risk of reject is r of alpha k plus 1 by x, the limit of k equals to 1 to k of lambda p of ck by x equals to lambda. And the risk of choosing class Ci is r of alpha I by x equals to the limit of k not equals to I to p of ck by x equals to 1 minus p of ci by x. So choose ci if p of ci by x is greater than p of ck by x, and it rejects otherwise, where choosing ci shows k does not belong to I and p of ci by x is greater than 1 minus lambda. Discriminant functions. Classification can also be seen as implementing a set of discriminant functions gi of x where I equals to 1 to k, such that we choose ci if gi of x equals to max k gk of x. We can represent the Bayes classifier in this way by setting gi x equals to minus r of alpha I by x, p of ci by x, p of x by ci multiplied by p of ci. And the maximum discriminant functions corresponds to the minimum conditional risk when we use the 0 or 1 loss function. Now, this divides the features space into k decision regions R1 to Rk, where Ri equals to x by gi of x equals to max k gk of x. The figure here is an example of decision regions and decision boundaries. You can see this portion is a reject between the different classes and the decision regions and the decision boundaries as being depicted here. K equals to two classes. When there are two classes, we can define a single discriminant. Dichotomizer, where k equals to 2, versus polychotomizer, where k is greater than 2. G of x equals to g of 1 of x minus g of 2 of x. We choose C1 if g of x is greater than 0, and we choose C2 otherwise. Log sorts represents log of p of C1 by x by P2 of C2 by x. We now generalize this to utility theory, which is concerned with making rational decisions when we are uncertain about the state. The probability of state k given evidence x equals to p of sk by x, utility of alpha I when state is k is to uik. Expected utility is given as follows, where we choose alpha I if e of u of alpha I by x equals to max j eu of alpha j by x. Association rule. Association rule is an implication of the form x tends to y, where x is the association rule antecedents and y is the consequence of the rule. One example of association rule is in basket analysis, where we want to find the dependency between the two items x and y. Say for examples, people who buy or click or visit or enjoy X are also likely to buy or click or visit or enjoy Y. A rule implies association, not necessarily causation. Association measures support, confidence, and lift. Support is X tends to Y, where probability of X comma Y is equals to number of customers who bought X and Y by the number of total customers. Confidence X tends to Y is probability of Y by X equals to probability of X comma Y by probability of X is equals to number of customers who bought X and Y by number of customers who bought only X. Lift X tends to Y is equals to P of X comma Y by P of X multiplied by P of Y. That gives to P of Y by X by P of Y. A priori algorithm. Finding frequent item set, that is, those which have enough support, and converting them to rules with enough confidence by splitting the items into two as items in the antecedents and items in the consequent. For X, Y, Z, a three-item set to be frequent, have enough support, gives XY, XZ, and YZ should be frequent. If XY is not frequent, none of its superset can be frequent. Once we find the frequent k-item set, we convert them to rules x, y tends to z, and so on, and y tends to, x tends to y, z, and so on. Thank you.